my first thought in this direction dates back to 1985. So at that time I was working as a postdoc in the group of Dietmar Möbius and Hans Kuhn in Göttingen. And they had a very interesting scheme to detect single molecules by FRET, by energy transfer, having a large aggregate that would collect the energy and transfer this energy to an acceptor. And so the acceptor would quench the whole energy of the whole aggregate. So there was an amplification mechanism in this way that would allow you to detect one acceptor molecule by the lack of fluorescence of 10 to the 3, 10 to the 4 donor molecules in the aggregate. So that was the first step in this direction. Independently, I was thinking about scattering and reflection. And my first idea to detect a single molecule was actually to rely on scattering. And as you well know, this is no easy job. And eventually, in the course of 86, 87, I thought it was safer and easier to switch to fluorescence, with the success that you all know. I must confess that at that time I knew absolutely nothing about it, so it was completely independent. I got a lot of inspiration from the STM. This was, of course, common knowledge. It was highly publicized at that time. It was shortly after the discovery, Nobel Prize on this. And obviously, when you finally can see atoms with a tip, with a sort of super record player, you think, why not use light, which, as we know, is also a way to record information. And so came immediately the idea, could we do that, see single atoms or single molecules by light? And actually it was done before in the gas phase with single atoms in atomic beams, and at about the same time with trapped ions. And so the next step was, can we do that in condensed matter? So no previous knowledge about the earlier effort of Hirschfeld and Billion and Martinsen, many previous researchers who obtained nearly single molecule results, but I was completely ignorant of that at the time. In 1985, I was completely molecular crystal spectroscopy community. And after my postdoc, I moved rather to the high-resolution community, the whole burners, high-resolution spectroscopy of solid solutions, so low-temperature physics. So until 1995, we were completely embedded in these two communities. On the one hand, molecular spectroscopy in the ensemble, conventional ensemble averaged sense. And later on I became a member of this whole burning community, which is still an ensemble measurement, but the ensemble is reduced very much by frequency selection. So it was still the community of molecular spectroscopy in general. Of course, different people moved at different times, as you well know, but the really smart and experienced people already realized very early on from the early 1990s that there was a huge potential for biomedical science in general. And Jan Schmidt, for example, my predecessor in Leiden, already set up a European network back in 1994, yes. Which had some, one of the goals was really to prepare the way to go to biophysics. And then later on, I think the bulk of the community really started to move there with the young people switching fields from spectroscopy to biophysics and biology, rather in the late 90s and beginning of 2000s. And then the single molecule biophysics field matured in the early 2000s, and I think now it's more or less it's a technique that has percolated to many labs, but I don't identify it anymore as a field by itself. People don't study single molecules for the sake of single molecules. It's just a technique they use to solve their biological problems. I think this morning at this conference we had the story of near-field optics, and that's obviously one of the big hopes of the 1990s that has failed so far, at least, to bring its promise. The technique has been exceedingly complicated to operate and slow to operate, and it has been overtaken by the far-field microscopy techniques as we know them. It's one of them. Many of the questions I had in the 90s on solid-state dynamics are still open, mostly for lack of interest by the community, because people prefer to go the whole way to bio and don't stop between single molecules and single cells. They don't stop in a single nanometer environment in soft matter, for example, although there are many problems that could benefit from single molecule approaches. Well, I think there are two reasons. The first one is, of course, the huge imbalance between the number of questions and the importance of questions that are still open in biology. It's a huge continent that we barely scratched the surface. There is so much unknown and complex that we don't understand. And that's part of the question compared to, for example, condensed matter. There are still many open questions, but not as much as in biology. On the one hand, on the other hand, I think the field of solid-state studies and liquid-state studies, soft matter studies, is still underrepresented in the community of single molecule researchers, and to a large extent is due because most people prefer to go the whole way to biophysics or biology even, instead of stopping in the midway. It's more, I think, mostly a cultural problem than a scientific problem. I have ambiguous feelings about nano-optics. Well, some 20 years ago, I know that you like this term nano-optics, and to me it was an oxymoron, a contradiction in terms. Because for me, optics, I was seeing optics, as we heard again this afternoon, I was seeing optics as a spatial concept. Optics is everything that happens to radiation at scales larger than the wavelengths. So in this sense, nano-optics cannot exist, right? But of course, you can see optics in the frequency regions. If you think of optical photons as photons with a frequency of 10 to the 15 hertz, thereabouts, then of course you can do, of course, all kinds of interactions at all distances. And then nano-optics, of course, takes its full meaning. So I think nano-optics is really the field of interaction of light at optical visible frequencies, or UV visible frequencies and near-infrared frequencies, with matter at all scales. So in this sense, of course, nano-optics. I see it as a field. Maybe it's again taking the path that single molecule detection has taken 20 years ago, towards a technique that gets used, and now we have to use this tool to do nice science. It's true. I'm a little bit disappointed that so many groups have left low temperature, high resolution spectroscopy, because I love this field very much. A few groups, yours in particular, are pursuing this path, which is a difficult one and an expensive one. But it's a beautiful one. It's a way to keep a well-defined system in well-defined conditions doing. It's a nice way to connect physics with the complexity of matter, let's say, chemistry. So it's a nice interface between quantum mechanics and chemistry, making molecules, using molecules, making materials, using materials. And I think we have a tendency these days to forget about these very basic questions. Some of them have been solved, many of them are still open, and it's a bit of a disappointment indeed for me that so many groups go to applications, as I see biophysics as a sort of application, without stopping a little bit to think a little bit about the basis of light-matter interaction with complex systems, and which indeed is a preparation of the next wave of experimental advances that will allow even more progress eventually all the way to the bio and medical sciences. So I hope there will be a correction to that in the future.